Functional theory. I think many of you, or maybe almost all of you, are using DFT for your calculations. So if you want to have some proper understanding what exactly density functional theory is, so here you can see, if I tell it so here you can see there are three terms: density, functional and theory. So first you have to learn what exactly do you mean by density. Sorry. What is the functional? What do you mean by functional? And what is that theory connecting density and functional, which has become a kind of workhorse for any type of electronic structure calculation and also in other places. So we will have to start from the scratch. What exactly do we mean by density? Okay, so we will start from very basic level so that you don't have any kind of confusion. So you have to learn what is density matrix, and what is a density functional. Okay, so we'll start from density. So we'll start from the simplest possible system. Let's say you have a single electron. Let's say in orbital AR with spin half, like it can be up spin or down spin. And this R vector, as I told you before, it means a point in a three-dimensional space. So R is the radius vector, so which takes care of three variables r, theta and phi. That's why you have that arrow at the top. Now, the corresponding probability density here. In general, what we do, we talk about space spin coordinate x, and x is your r, comma sigma. Sigma is the spin coordinate and r is your r theta phi. Okay, so x is space spin coordinate. Together we are having this variable. So rho x would be some chi sigma, let's say. So this may be alpha or beta. Okay, this is a spin function, and this one is your ordinary orbitals. So that means basically this is your spin orbital, nothing else, isn't it? This is the, sorry, this is not rho x. This is psi a x. This is your spin orbital. We have already learned, isn't it? This is spin orbital. Now, what is the corresponding probability density? Probability density would be, say, rho x would be psi a star x, psi a x. That means it is your AR mod square and chi sigma mod square. Okay. That is your probability density. Now, suppose if you have a very small, let us say, volume element between x to x plus dx, which we will call that probability of having the electron in dx. Dx means between x and x plus dx in that volume element. Okay. That probability would be your rho x dx. Okay. Now, suppose if I want to tell that probability of getting the electron in dr of any spin. So, I do not bother about spin, only where shall I get the electron. We do not want to specify whether alpha spin or beta spin. Then it would be just that probability would be rho r dr, and that would be your dr rho x dx, or basically as d sigma. As sigma you have only step values alpha, beta, etc. So, I can always write this dr sum over sigma rho x. Okay. So, that means I am adding it for alpha spin as well as for the beta spin. So, I can write it like this. Now, suppose there are two electrons and I say that electron 1 probability of getting that in dx1 and electron 2 probability of getting that simultaneously in dx2. Okay. So, we will have to find out now using a two particle wave function. Okay. So, first we will take a general situation like many electron case, and we will treat electron by electron. Okay. That means you have psi x1, x2 up to xn. This is the many electron wave function. Now for this general situation, suppose if I want to get the probability of getting electron 1 in dx1, electron 2 in dx2, electron 3 in dx3, up to electron n in dxn. Okay, that means probability of electron 1 in dx1, electron 2 in dx2, up to electron n in dxn simultaneously. Then that one would be your rho. I'll bring rho later. Psi x1, x2, xn, psi star x1, x2, xn, sorry. And then you have dx1, dx2 up to dxn. Okay, this is the probability. Just simply we have extended the dimensionality. First we had a single electron, now we are talking about two electrons. Now let's see if I say probability of having electron 1 in that n electron system within the volume element dx1 without bothering about the position or spin of the other electrons. That means the other electrons may be anywhere. Okay. Others anywhere. So this one would be integral psi x1, x2 up to xn, psi star x1, x2 up to xn. Then you have dx2 up to dxn, and this should be multiplied by dx1. Okay. So what we have done? We have integrated over the coordinates of remaining n minus 1 electrons. So if I integrate this, only the probability corresponding to electron 1 will come out. Okay. So that means what we are trying to do now, you can see, although we are within a many electron framework, we are focusing on only one electron. Okay. And trying to get the corresponding probability. Now if I say that electrons are indistinguishable, okay, so I cannot tell which one is electron 1. So probability of finding an electron, if I say, in dx1 and others are anywhere, then you can see the probability of getting first electron is same as the probability of getting second electron, and same. There are n such terms you will get. That means you have to multiply this by n. Okay. And now I will write this as dx. Okay. So in dx, because there is no say connection with electron 1, so I am writing dx. In general, between x and x plus dx, what is the probability of having any electron, and the others are anywhere. Okay. So this is the corresponding probability. So this is your probability density. Look, this one is your probability density, isn't it? Or we will call it, say, single particle probability density. Okay. Now suppose even I will write this as, let's say, rho x, single particle probability density. Now suppose if I don't want to talk about the spin of that electron, as we have done before, so we will tell that probability of finding an electron with others anywhere, irrespective of the spin. Then what I have to do? I have to, say, keep like dr over here, integral irrespective of spin. Rho x and then d sigma, isn't it? This probability of getting the electron between r and r plus dr now. Okay. So this probability in dr, irrespective of spin, that I can get simply integrating over the spin variable. But you see, previously I did this for the single electron, but now also we are doing in the single electron, but in a many electron framework. Okay. So we have integrated over n-1 particle coordinate the corresponding wave function into its complex conjugate. So that means ultimately we are getting the features of only one electron, and that too, because of indistinguishability, we consider any electron. And this one, we will write it as dr rho r. So this one we will call single particle density. Sometimes we call it single particle spinless single particle density, but generally if you don't mention anything, we mean this one, rho of r. Okay. So this is your single particle density is nothing but actually your electron density function, which we measure generally as an experimental quantity using crystallography. It's the same single particle density, single density, only density, electron density, these are all same stuff. Actually, when we talk about density functional theory, basically we mainly focus on this density. Do you understand? So you know how we have derived this density. If you don't know this whole exercise, you will never be able to understand DFT. Okay. So this is your density. So how you do it? You have many particle situation. You take psi star psi dx, that would be the probability of getting the electron 1 in dx1, electron 2 in dx2, etc., etc. Then you say that you consider only electron 1 in dx1, rest may be anywhere, integrate over another remaining n minus 1 particle coordinates. Because of indistinguishability, multiply by n. If you don't want to know the spin of that one electron what we are considering, then integrate over sigma. That quantity what you are generating is your single particle density of the density functional theory. Is it clear? Okay. We will go further to somewhat difficult situation. If you have any confusion, tell right now. Okay. You see, what we have done, we are going expanding the space, shrinking the space, but original what we have learnt in the first postulate of quantum mechanics, the Born's interpretation, the probability density, if you know the wave function, how you define, we are not using any extra information, okay, other than we are defining something, nothing else. Now let us say we consider two electrons simultaneously. Sometimes it is required. What do you mean by two electrons? First we will consider simultaneous probability of finding electron 1 in dx1 and electron 2 in dx2. What is the simultaneous probability? Okay. This would be dx1 dx2 integral Now, here you can see I am keeping dx1, dx2 outside, integrating over dx3 to dxn. Perfect. Then what will you do? We will say again electrons are indistinguishable, so we do not know. So we will say the probability of getting one electron in dx1, another electron in dx2. Okay, rest anywhere. So simultaneously I will get one electron in dx1, one electron in dx2. Okay. So finding an electron in dx1 and another in dx2 simultaneously. So what I have to do here? Now I have to multiply by n into n minus 1 dx1 dx2 this one, because the first electron can be put in n different ways, but simultaneously I am going to calculate. That means first electron is already fixed. Now I can have only n minus 1 possibility for putting, that's why n into n minus 1 different ways of putting them there. Okay. Now I say we don't bother about the spin of those two electrons. They may be of any combination. Any combination means up up, it may be down down, it may be up down, or it may be down up. All possible combinations they are allowed, any one of them. We don't care about the exact spin combination of the first electron and the second electron. First electron is in dx1 and second in dx2. Now I will say first electron in dr1, second electron is in dr2. Okay. That means if I call this one as rho 2 x1 x2, then I will integrate over this. Say this one would be dr1 dr2, and then you have integral. So this is irrespective of spin. Rho 2 x1 x2 d sigma 1 d sigma 2. Okay. So if you have integrated, we don't have any specific history, so it can be of anything. So this quantity, so this one we'll write it as rho 2 r1 r2. The other one was rho of r or rho 1 of r1. This is rho 2 of r1 and r2. So what does it measure, this rho 2 of r1 or r2? Basically it is the probability density of getting one electron in r1, another electron in r2, irrespective of the spin combinations. Simultaneously, if you want to get what is the corresponding probability density. So this is called pair function. Or two particle density. So you see, the first one we told single particle density, this one we will call two particle density. So if I ask you what is the definition of single particle density, can you tell, any one of you? What is single particle density? Just now I explained. Louder. One electron in R1, irrespective of spin, other electrons anywhere. You have to tell all this. Okay. So that is your single particle density. Then what is your pair function of two particle density? Tell. What is two particle density? Probability of finding an electron in dr1, another electron in dr2, others anywhere irrespective of spin. that probability density is your two particle density. Okay. So now you know at least partly in density functional theory what is the density, and depending on your problem you require one particle and two particle densities. Actually, if you solve atomic, molecular, etc. problems, you never need higher than a two particle density. If you talk about some typical physics problem involving three centers, etc., because all possible interactions, they are either say one particle problem or two particle problem, nothing else. You say Coulomb interaction, you say gravitational interaction, maximum two particle, Q1, Q2, M1, M2. Okay, Q1, Q2 by R square, let's say that is the force, or M1, M2 by R square, that's the corresponding gravitational force with some constant, proportionality constant. You never need like more than two particles. Perfect. So fortunately, most of the problems you can boil down to your one particle framework, but you need the two particle function in some cases, like if you have to treat let's say the Coulomb interactions, that requires your particularly two body Coulomb interactions. There you would require this quantity. Okay. So now we will see how you make use of, you just make use of these density functions. What is the time, by the way? 10:43. Okay, we'll see. So how you make use of this? First we'll consider a single electron problem. Okay. Say suppose I want to get any property of that system. So any property, let's say F. So in quantum mechanics, you have a corresponding operator, isn't it? And if you want to measure, let's say, that quantity, you get in terms of the expectation value. So expectation value would be your wave function F operator, and if it is normalized, this part is generally 1 for the normalized functions. Okay. Now I will just show you that your main aim, you remember, the psi contains several variables in general case, but if you want to focus on one electron, you have to integrate over n-1 particle coordinates, etc., that we have learned. Now this integral, so your main job would be to find out this integral. Okay. What is this integral? So this is your integral psi star f, psi d tau, this quantity. If f operates on psi, it will generate a new function. But your definition of density requires psi star psi to be present. Do you understand? But if f already operates on psi, here it will give a new function. So your psi star into that function cannot be reduced to your density, whatever we have defined so far, except if f is a multiplicative operator. So what are the multiplicative operators? Can you tell? See your electron nuclear attraction operator. That's a multiplicative operator, minus z by Ri, or sum over alpha minus z alpha by r alpha I for a molecule is multiplicative. In two body, say if I call half, say if I call this minus, so this is your V electron nuclear R is minus z by Ri, so for one electron let us say Ri, or minus sum over alpha z alpha by R alpha I, this for the molecule. Electron repulsion is like half I j I not equal to j 1 by Rij in 1 by 4 pi epsilon 0 unit. So this is also multiplicative, although it's a two body operator. So this is a multiplicative. So if they are multiplicative operator, like your say, so VE is a function of Ri Rj. Okay. So now, if f is a multiplicative operator, that means you have to get, if you want to get the expectation value of the Hamiltonian, you have to get the expectation value of kinetic energy operator and all possible potential energy terms. If they are multiplicative operator, there is no trouble. Okay. That means for multiplicative operator, so you can do this. You can take your potential before and take psi star psi. That means you get here your rho. Okay. So you can see this is pretty easy. Then you operate F on the rho. No trouble. That means you multiply with the density and then integrate. But what will you do with the kinetic energy operator? You see, if I call the kinetic energy operator, that's minus half del square or del I square if you have ith electron. This is your kinetic energy operator. Okay. If your F is the kinetic energy operator, it is no longer a multiplicative operator. So it is now difficult to convert it to the density. Perfect. Do you understand the problem? So now what will you do? If it is not a multiplicative operator, so here you take a trick. The trick is integral F psi star x prime psi x dx so, and here you have x prime equal to x. So what are you doing? You are telling that the variable of psi prime, sorry, F is operating on psi. Sorry. Okay. I have changed only the variable of psi star. So out of this product now, this F will operate only on psi of x. After this, I will change before the integration. I have to integrate also, isn't it? Before the integration, I will change this variable. Do you understand this? So I will change the variable before the operation of F, but I will again consider the same variable. I will put x equal to x prime before integration. Okay. Now this quantity here I will call rho x prime. Or if I say rho x semicolon x prime, if I integrate over d sigma, I will get rho r prime. This quantity I will call single particle density matrix. Okay. And this one I will call spinless single particle density matrix. And here you can see the diagonal element of this density matrix x is nothing but your rho of x. Okay, because if you put x equal to x prime in this definition, you are getting basically rho of x, isn't it? And that is nothing but your diagonal element of the density matrix. Perfect. If you want to go for two particle case, you get immediately your, let's say, n. So in this case, obviously for a single particle I told, if you go for many particle case but single electron, single particle density, then you have to do it. This rho x prime would be n integral psi x1 prime x2 xn psi x1 x2 up to xn and dx2 to dxn. Okay, and similarly you integrate over spin and do whatever you want. So that quantity would be your rho x prime for single particle density matrix for n body problem. Okay, the way we developed, and here also as you can see your diagonal element should be rho of x. Okay, if I take x equal to x prime, it is nothing but your rho of x, and similarly for rho of r. If you integrate this quantity over sigma, so you get only one sigma is left, because all other sigma and x all are integrated out. Okay. So this one is your single particle density matrix. Two particle density matrix in this case, so two particle density matrix in this case would be rho x1 x2 x1 prime x2 prime, this is equal to n into n minus 1 integral psi x1 prime x2 prime, and rest are as usual xn, and then psi star x1 x2 up to xn, and then you have dx3 to dxn, and this is your two particle density matrix, and you get spinless two particle density matrix if you integrate over d sigma 1 and d sigma 2. Okay, and here also your diagonal elements should be the corresponding old ordinary density functions. So you have a density functions and density matrices. There are two different things. And if you want to find out the expectation value of kinetic energy operator, you cannot do it with density function. So you have to do it with density matrix. And for, let's say, electronuclear attraction, one particle, say single particle density is sufficient, but for Coulomb repulsion, electron-electron repulsion, you need the corresponding two body density matrix. Okay, so I think I stop here, and then some example I will show you, and then I will go to the functionals. So we have explained density and density matrices. So do you have any confusion? Because you cannot understand DFT if you don't know the density itself. So density means so many different things. Depending on your problem, the situation, you have to use the proper density. Do you understand? Okay, so now we will see how we make use of is various density related functions like density function, density matrix, and then we will talk about density functionals later. So if you want to calculate, let's say, energy is the expectation value of the Hamiltonian operator. Let's say we have in general many electron problem. Okay, that means this quantity is your psi h psi, and if it is normalized, this quantity is just 1. So try to understand, say like term by term. So this is minus half sum over I del I square, and your wave function is basically psi x1 x2 xn, but unless we talk about any specific spin dependent operator, we will integrate over all spin coordinates. That means I mostly talk about R1, R2 up to Rn. And remember, rho of R is n integral psi star R1, R2 up to Rn, then psi R1, R2 up to Rn, and then you have dr2 to drn. Okay, and rho 2 R1 R2 is n into n minus 1 integral psi star R1 R2 up to Rn psi R1 R2 up to Rn, and dr3 to drn. Okay, and another thing I have to do, rho r prime is n psi star R1 prime R2 up to Rn psi R1 R2 Rn, and dr2 to drn. Okay, this is your say single particle density matrix. Now if I want to go for the corresponding two body density matrix, sorry, R1 R2 R1 prime R2 prime, this would be n into n minus 1 integral psi star R1 prime R2 prime raised up to Rn, and then you have psi R1, R2 up to Rn, and dr3 to drn. Okay, this is your two-body density matrix. This is something what we already learned. Okay. So this one, so you have minus half del I square, then you have minus, I am writing for atom, let's say, sum over I z by Ri plus half Ij 1 by Rij. Okay. This is your kinetic energy operator, this electronuclear attraction operator, and for molecules this term would be minus sum over alpha sum over I z alpha by R alpha I. This for the molecules, just only you have additional summation over the nuclei. Okay, because you have to consider each nuclei, each electron, all possible combinations. This is your electron-electron repulsion term. This term, I will come back to this later. So, suppose I write this one or that one, whatever, as V of R, in this case V of Ri, let's say, and this one, let's say I am writing G of, or simply Ij. Okay. This multiplicative, this is differential. Now you see, I will remove this one anyway, but we will make use of them. Now I will introduce one very important concept over here. You see, what we are doing here, within Born-Oppenheimer approximation, we first freeze the nuclei, construct electron-nuclear attraction. For that I have to know the exact locations of the nuclei, but I am not changing them. Then I put it there in the electronic Hamiltonian, like this is your electronic Hamiltonian. Then I solve electronic Schrodinger equation. Okay. Then we go back again doing something to get the nuclear part, etc. But now our current problem is just to solve the electronic problem, electronic structure calculation. Electronic Schrodinger equation, but that needs the input outside the electrons. That means I have to get electron nuclear attraction which is external to your electronic problem. Okay. So this is something, it will vary from system to system and geometry to geometry of the molecule. Okay. And this one we will call in general external potential. In DFT you will hear it again and again, this is called external potential. and number of electrons, let's say I equal to 1 to n, for each electron the operator is same. It would depend only on how many electrons are there. This form is same, and if you know the number of electrons, you can immediately calculate this form, because this is just 1 by R12 you add. What does it mean? It means n and this small Vr, these two variables are sufficient to fix the Hamiltonian. You don't need any other information other than n and Vr, where Vr is the external potential. Now, when I say external potential, I must qualify this. Suppose if you place your molecule in some external electric field, magnetic field, in presence of some solvent, you are heating it within a heat bath, all these can be added to your external potential. But if nothing is there, a simple molecule without any external perturbation, it is your electronuclear attraction potential. Is that clear? So you can see that if you know the external potential and if you know the number of electrons, you know the Hamiltonian, and if you know the Hamiltonian means you know everything about the system. Because after that you solve Schrodinger equation or whatever equation, get the solution and then calculate whatever you want. So n and Vr will completely fix the Hamiltonian and fix the set all possible available information about the system. Okay. So this is something very, very important in understanding DFT. N and Vr are crucial. Now, if I want to find out this expectation value, so suppose if I call this as my T operator, this is my V En operator, this is my VEE operator. Okay. One electron problem. So this one would be this, isn't it? This expectation value, now all those integrals of this will turn out to be this, isn't it? Because these are one electron operators. So single particle density matrix. Remember, here you have to take density matrix. Why? Because the kinetic energy operator is not a multiplicative operator. What about this one? This one would be integral VEN operator rho r dr. Okay. This again one electron operator. At a time I am taking only one electron, and multiplicative. So I get single particle density there. Don't get confused. If you get confused, you just tell me that I am not getting it. Okay? Can you tell what would be the last one? So this one would be plus double integral VEE rho 2 R1 R2 dr1 Okay. So you see that I need all three of them, but nothing else. No three body, nothing. Okay. And as I told you that within this external potential, you can add all possible external perturbations. The meaning of this is all of them will go here in the same format. So you can write down very easily. Nothing else is required. Perfect. So now you can see, I will tell you later, the way I have written, this one is a proper density functional. But this one, we'll see what is its fate. This one in general we call it a density matrix functional, but that is difficult to handle. Okay. So there we need to have the density functional theory so that I can convert this also to a density functional. Okay. So this one we have not brought anything about density functional theory. This standard wave function based approach, only thing I have rewritten everything or recast everything in within the density matrix, etc. But if you have to go to DFT, you have to write everything in terms of single particle density. So first of all you have to just ensure that single particle density contains all information, then how to write them. Okay, so these are the two important questions that we will have to understand. So here you can see this is not a density functional per se, it is density matrix functional. So as good as I am doing it with the wave function, nothing else, isn't it? Only written in that language, that's it. Similarly, here you have the two body matrix, two body function. So that's also not a standard density function, because when I say density function, I have to get that spinless single particle density function that is required. So now we have to learn what is a functional. If you don't know that, obviously the whole game is incomplete. What is a functional? First of all, many people they tell that it is a function of a function. No, that is totally wrong. Functional is not a function of a function. Because function of a function is also a function, not a functional. A functional means it's a correspondence between a set of functions to a set of numbers. That means if you tell function of a function, let's say if I say e to the power sin x, this is a function of a function, but still it is a function. It is not a functional, because it's a function, it's not a number. Functional means it's a correspondence between a function and a number. Okay. So how will you define? So before that, let me tell you what is the basic difference. Suppose if I have a function of y as a function of x. This is a simple function. That means what? Say if I get for any x value, I will get some value of y. Now if you connect, I get a curve. This is your function. Okay, I get a curve simply. This your y may be, let's say x square, it may be sin x, it may be e to the power x, it may be log x, whatever. That means for each value of x, there is a value of y. So it's a correspondence between one set of numbers with another set of numbers. Okay, for a given value of xi, you have a set of values for yi. So that is the correspondence or map, a set of numbers mapped with another set of numbers. Okay, so a function or a curve is basically a map between, say, two sets of numbers. Now suppose you think about it, this is your what we can call a coordinate space. Okay, this is your coordinate space. Now think about this, that we are talking about a function space. Say here that means what? Now I have functions as the elements, independent variable, not numbers. And for each of them I get a number. Then this curve or this particular stuff I will call a functional. You can see it's a number, it's not a function of a function. So mathematically, how, so this one I will call a functional. Okay. Now suppose I have a function of x, y and y prime means dy dx. If I integrate this, you see x is now a dummy variable, it has no meaning and I am integrating over it. It is a definite integral, that means it will generate a number. Okay, after integration you will get a number. If you want to change the number, what you have to do? You have to change only the function, otherwise you cannot change this. So this one is a functional. Do you understand? So if I write it in this form, I will call it a functional. If I independent integral, obviously that will not be a functional because I have to get a number, so it must be a definite integral. Okay? So if I want to write, let's say, energy density functional, first of all, let me tell you this energy functional, what we have shown. This is what? You have a definite integral if you change the trial function, the number will change. So in the variational, say, principle when we studied, you remember we talked about energy functional. So energy functional, why it is so? Because it is exactly of the same form. Okay. If I do this, I will get the derivative of that also. So that means you get, it's a dependent on the function, its derivative and so on. Which derivative, first order, second order? You see, when you talk about various types of functional, GGA, meta GGA, you will see some are first derivative, some are second derivative, they are all considered. That, if time permits, I will tell you something like that. Okay. So this is just a functional. If I want to write it as a density functional, then what I get? Suppose if I call this energy as a density functional, then it would be, say, integral your a to b, whatever may be your limit, say energy as a functional let me write it like E as a functional of rho r rho prime dr. Okay, so this would be energy density functional. Okay. Now we have to learn functional derivative. For understanding this, you have to learn what is called calculus of variations. Have you ever heard of this term, calculus of variation? Calculus of variation. You don't know. So functional derivative or variational derivative. You see, if you have y as a function of x, for checking maxima, minima, etc., you have to know the first derivative, second derivative of y with respect to x. But in case of functional, obviously the derivative would be with respect to function. Instead of varying x there, here you have to vary y, the functions. And then the change in the functional, like when you are doing variational optimization, basically what you are doing, you are varying your trial function and then energy functional is being varied. So there you are basically taking functional derivatives. So functional derivative, suppose if I call del j y, del y, you remember ordinary derivative we take with d. Functional derivatives we write with this type of delta. Okay, in DFT everywhere you will see this, otherwise you will never understand it. This is called functional derivative of that functional with respect to the function. So this is your f y minus d dx of f y prime. So okay, this is the definition of the functional derivative. That means you take the derivative of that f with respect to y minus d dx of f y prime. I will show you some example maybe in the next class. I will start from there. How to calculate the functional derivatives. Is d dx of f y prime. Okay. Now, suppose if it is your energy functional, this is your energy, this is your density. You are varying with respect to density. There is the trial densities, etc. Now suppose what you have to do within a variational principle, What is the variational principle in this case? Okay. So we will see the variational principle. Suppose if you want to, you have a class of your functions y. What is the necessary condition that for a given y, there would be an extremum of j? Okay. So that is, you know the necessary condition there is the first derivative is 0, and that is the standard way you could tackle the variational principle in ordinary wave function based quantum mechanics. But here what you are trying within the density functional approach, in this case you have to go for the functionals. So you have to find out the necessary condition that a particular y, what is the condition the y must satisfy so that j of y may have some extremum. Okay. This is given by, variational principle is given by Euler's principle. Euler's relation that tells that your del y must be 0. Okay. That means it's no different from ordinary one. There you tell the first derivative is 0, here you tell that functional derivative is 0. That's the Euler's principle. Okay. So you calculate the functional derivative, and this equation is called Euler equation. But sometimes you have to have certain constraints that not all y's are acceptable solutions. So like I will tell you one example. So you have energy functional E rho. Okay. You have to find out the minimum value of, let's say, energy. Then what you have to do? You have to do del E rho, del rho, that should be 0. That is your Euler's condition, and this is the corresponding Euler equation. But you tell that when you vary the density, you must make sure that rho dr must be n. You do it immediately. You have the definition of rho. If you integrate it once, what do you get? N. Because rest integral is 1, isn't it? So this is what we call normalization constraint, that the wave function would be normalized if the first derivative, say single particle density rho r dr integral must be n. Okay. So if this condition is not satisfied, but suppose you get some density which is minimizing your energy via Euler's condition, that is not acceptable. So you have to do what is called constraint variation. That is, physics students who have learned classical mechanics any day, they must be knowing what is called a constraint variation. Then simultaneously you are varying this, but one constraint must also be satisfied. And those constraints are added via what is called a Lagrange multiplier. Okay. Maybe you have heard this term somewhere before. So this, what you get, the del E rho minus mu integral rho dr minus n. Remember that this must be 0. Okay. This is called Lagrange multiplier. This is Lagrange undetermined multiplier. And this quantity should be 0. Or if I do it because delta of n is 0, n is constant, so what you get is del E. So you see the change. So this is what we call Euler equation, and this one we will call Euler-Lagrange equation. Because you have a Lagrange multiplier, del rho equal to mu. Okay. Where mu is the Lagrange multiplier associated with the normalization constant. But in chemistry, you will see later that this mu has very important like reactivity description within the mu. This mu, we call it electronic chemical potential, and which is the negative of electronegativity. So this will bring in later, but at this moment when you solve this equation, you will get the, knowing the energy functional, if you can construct the energy functional and take the functional derivative, put that to be mu and solve it, you will get the density. And if you get the density, you put it back, you get the energy also. And all other properties would be basically density functionals. And in order to prove that, what you need is you have to learn that density contains that information. You have to solve, you have to understand the Hohenberg-Kohn theorems. That we will do tomorrow. There is a class, so that we will do tomorrow. Okay. So I stop at this point today. So I have told you about single particle density, two particle density, density matrix, and density functionals also. Okay. So I have more or less prepared the background so that you can appreciate DFT, which I will do it in the next class. And once again, I am telling you repeatedly, if you have any confusion, you ask me immediately.